The topic of this section is directional derivative. Directional derivative is a generalization of the partial derivative. In partial derivative, say for a function of two variables at a point, we consider the derivative with respect to x when we change x only and y is constant. Or when we change y only and x is constant, then we consider this direction. Well, but sometimes it's important to consider the change of the function value if we change the arguments in a general direction given by some vector a. So the directional derivative denoted by capital D of a function f of two or more variables at the point x in the direction or along a vector a is given again by the limit for h going to 0, and here we have again change of the function value divided by the small amount h. And now we evaluate f at a new point which is x plus h a minus the function value at the point capital X. If we look at this argument, then if we have the point capital X and if we have the vector A, then when we add the vector to the point, then we jump from this point to this one. But if we multiply the vector by some scalar h, then we resize this step. Well, and we are interested in small h. So we move from this point in this direction, but only a very small distance. And we compare the new value with the old value and divide by this parameter h, and then if this limit exists, it is an important object and we call it directional derivative. It is also sometimes denoted by nabla af. Okay, let's consider some example. Well, perhaps we could relate the directional derivative to the partial derivatives. If we choose the vector A, given the direction, to be vector 1, 0, then the partial derivative, the directional derivative along this vector is the partial derivative with respect to x. And if we choose the vector to be 1, 0, then the directional derivative along this vector is the partial derivative with respect to y. We usually assume, or we usually want, the norm of the vector being 1, so that the vector defines only the direction and does not influence the derivative itself. So consider the function fxy being arctangent of the product x times y, and consider the point 1, 2 Well, I sometimes use the column notation, sometimes I use the row notation. In this situation, this does not make a difference. And consider the vector 3, minus 4. Let's call it B. Okay, also as a column. So we want a vector A, which is parallel to B in the same direction and orientation, but with the unit norm. So first we compute the norm of B, which is the square root of B1 squared plus B2 squared which is 3 squared plus 4 squared, which is 9 plus 16, which is 5. And then the vector A in this direction with the unit norm can be written as B divided by the norm of B. And then, well, now let me write it as a row vector, 3/5 and 4/5. Alternatively, we can write it as 1/5 times the vector 3/4. This is sometimes convenient to work with. So, the directional derivative of this function at this point along the vector A, well, this time we are going to compute this using the definition, but then I will show you a better approach, slightly more practical. So we have limit for h going to 0. The function value is arctangent. And now the point capital X is 1, 2. And we add h times the vector 3/5. Let me write it this way. h/5 times 3/4, which is 1 plus 3/5 of h and 2 plus 4/5 of h. And the function is arctangent of the product of the two arguments. This is the first argument and this is the second argument. So this is arctangent of product of 1 plus 3/5 of h times 2 plus 4/5 of h minus function value at x, which is arctangent of the product of the two arguments, which is 1 times 2 divided by h. Well, and now we want to evaluate this limit. Perhaps we can expand this multiplication. 1 times 2 is 2, and then we have plus 4/5 of h plus 6/5 of h plus 12/25 h squared, and arctangent of that. If h goes to 0, this goes to 0, this goes to 0, this goes to 0, this goes to 2, and we have arctangent of 2 minus arctangent of 2, which goes to 0. So we have the expression of the form 0 divided by 0. So to compute this limit, we can use L'Hopital's rule. The derivative of h with respect to h is 1, and the derivative of arctangent is 1/1 plus square of the argument. Well, now we can use this in the unexpanded form. 1 plus 3/5 of h times 2 plus 4/5 of h, and square of that. But this is a composite function, so we must multiply by the derivative of the inner function. And the inner function is this bracket, and the derivative is, this gives 0, this gives 4 over 5, plus 6 over 5, plus 24 over 25 h. Well, and this is already a continuous function, so the limit exists and is equal to the function value. And when we put h0, here we have 1 times 2, which is 2, plus 1 is 3. And here we have 10 over 5. Which is 2, so we have 2/3. Sorry, no. Well, I've forgotten this 2. So we have 1 times 2 is indeed 2, but we must take the square, which is 4, plus 1 is 5. So we have 2 over 5. No, 2 over 25. Okay, let me check this.